We are very pleased to have Karen Smith from the University of Michigan, who will tell us about values of the F-pure threshold.
Thanks, Carl, for the invitation, and thanks for everybody who came to hear me. For us, it's the last day of the semester with the graduation ceremony going on, so I feel grateful for anybody who's still willing to listen. Yeah, so I want to talk about some joint work that Adela Vrechu and I did in studying the F-pure threshold. So to keep things simple, especially since I can't write very quickly with the mouse on my Jamboard, I'm going to fix some notation and a slightly simpler situation. I'm going to always assume K is a field of characteristic P. And we're going to assume it's algebraically closed. You don't need that for most of the talk. And I'm going to fix a polynomial ring. So S is going to be a polynomial ring over that field. And the unique homogeneous maximal ideal of it is going to be denoted M. Is my handwriting okay? All right. So actually, a lot of what I'm saying is going to be fine for any regular local ring, which is F finite, where the Frobenius map is a finite homomorphism. But just to keep things concrete and simple, let's focus ourselves on a polynomial ring. And the F-pure threshold is a number. So I'm going to just say what it is and give some properties, and then I'll give the definition. The F-pure threshold is a numerical invariant. So it's a number, a numerical invariant that we're going to associate to a polynomial F, which is going to be a non-zero polynomial in our ring. And let's make sure it's not a, unit. In fact, I'm mostly going to be focusing very shortly on the homogeneous case. But like I said, a lot of this doesn't matter. We have a local ring, and it's a number. So it's a numerical invariant. And what it's supposed to be is measuring the singularity. That says measuring, sorry about the handwriting. The singularity, which is spec of S mod F at that point M. M is a point on that spec, right? So it's a local invariant. And, or if you like, you can think this is measuring the singularity of the variety cut out by F, which is sitting inside of Kn. Of course, I have n variable. Oh, that was an n. I have n variables. And the origin is the point of interest, just the way I fixed my maximal ideal to be the maximal ideal of the origin. And it measures the singularity of that variety at the origin. And this is supposed to be a characteristic P analog. Let me write it out. This is probably pretty familiar to most people in the seminar, but I'll remind you that this is a characteristic P analog of the log canonical threshold, which is a numerical invariant we can assign to a polynomial over the complex numbers. So I will define it, but I'm going to give you a couple of properties first, just to kind of get our head around it. Some properties of this numerical invariant are the following. So first of all, it is always a number in between 0 and 1. It's always strictly greater than 0. And by the way, I'm going to write FPT of F. And again, I'm always fixing a point. I'm fixing a maximal ideal where I'm looking at this F-pure threshold. It's a local invariant, but I won't write that in the notation. We have that we're always a positive number, and we're always less than or equal to 1. And then we can see why it's called the F-pure threshold, or one of the ideas of what it's measuring with singularities is that it equals 1. We know exactly when it equals 1, if and only if, so it's as big as it can possibly be, if and only if this ring S mod F is F pure, or equivalently, because I'm assuming this F finite situation is exactly the same as Frobenius split. You guys know what I mean by Frobenius split? What I mean is that the Frobenius map, maybe I should be kind. The Frobenius map S mod F, raising everything to the pth power, that's a capital F. So this is just sending a class R bar to R bar to the P. This is splits as an SRF module map. Every ring homomorphism allows me to think of the target ring as a module over the source ring. So we want to say that this splits as a module over that source ring. Everybody is, oops, my screen just disappeared. Okay, so that is what Frobenius split means. And this invariant is as large as it can be when that hypersurface cut out by F is Frobenius split. That follows from Fedder's criterion, for those of you who know it. Also, just some basic things. Oh, by the way, for log canonical threshold, we also have the same property, that the log canonical threshold is a number for when you have a polynomial over the complex numbers between 0 and 1, and it equals 1 if and only if the quotient or the variety cut out by F is log canonical. Another property we have, or maybe just to see an example, what does it do to a monomial? A monomial, just to kind of give you a sense, the F pure threshold of a monomial is the minimum possible value of the 1 over the exponents. Another fact is that the F pure threshold of a polynomial is always a rational number. So this one's a little bit harder theorem, but all of these things have been known for some time. By the way, I'm not writing names on this of who's responsible for all this stuff, but maybe I'll just say a few names. So Hara and Yoshida introduced Frobenius splitting of pairs, and Tagaki and Watanabe introduced the definition of F pure threshold that gives us this thing, although it didn't look at all like the way I'm going to define it in a moment. That came about later through work of Mustada and Tagaki and Watanabe, and me and Manuel and Mircea as well, kind of rephrased the way you think about it. And I will put the definition on the slide in a minute. But all of those people were involved in sort of developing this theory, proving some of these basic facts. This last fact here is about the F pure threshold always being rational, is due to me and Manuel and Mircea. All of the corresponding facts are true if I replace a polynomial over a field of Kerchik P with a polynomial over the complex numbers, and I replace the F pure threshold, or sorry, the F pure the word F pure everywhere with log canonical. Although there it's really easy to see that the log canonical threshold is a rational number, given resolution of singularities, which is not necessarily an easy theorem, but yes. Okay, so those are some basic properties that I wanted to mention. And now I think I should give you the definition, just so you have it. So let's define it. So again, I'm going to take my polynomial, which is not 0. And it's going to be not a unit. It's in the maximal ideal. And I am thinking in the polynomial ring or any regular local ring. Actually, it doesn't matter. And what I'm going to do is I'm going to think about, so on the side here, let me make a little thought bubble. What I'm thinking about is when I raise F to a power, that's an integer power, when am I in the ideal generated by the pth powers or the p to the eth powers? Remember, I'm in characteristic P. Sorry, does that look like a P to the E? This is the maximal ideal. This is the ideal generated by the elements of the maximal ideal raised to the p to the eth power, otherwise known as the Frobenius power of the maximal ideal. And we're going to think about when is f to the a in that Frobenius power. And so that's what we're thinking. And we kind of have a number line here. And if I fix E and I take A very large, I know that, of course, I will be, because the Frobenius power of the maximal ideal is an M primary ideal. I can eventually get in there. For large, if A is large, if A is very, very large for a fixed E, and if A is very, very small for a fixed E, but positive, I mean, or maybe another way to put it is that E is big relative to E, then we will have that f to the a is not in there, right? And what I want to do is I'm looking on a number line here at different values of A over P to the E. And I want to look at all of the numbers where A over P to the E satisfies that f to the a is in M P to the E. And again, when A is very large relative to P, we would expect this to happen. And so I'm going to take the infimum of those. That is my F pure threshold, or equivalently, it's maybe not 100% obvious that it's equivalent. So here's like the infimum. If A over P to the E is larger than this number, then those numbers will be in there. And if it's smaller, I can look at the supremum of the numbers where FA is not in there. So these two things are the same. The supremum and the infimum takes a little exercise to see that, but that is the definition of the F pure threshold. So the F pure threshold of F at the maximal ideal M is this real number. This is obviously a real number by the way I defined it. And like I said, it's a theorem that it's actually rational. So it doesn't look anything like the definition of log canonical threshold, which I will not remind you of, but it has to do with thinking about a log resolution of F, and it doesn't have anything to do with Frobenius or P powers or elements being in ideals. And so it's kind of interesting that this is an analog. Another way you can kind of think of it, but I put this in quotes and maybe intuitively. If I imagine working in the perfection of the polynomial ring where I allow P to the eth roots, I'm looking for F to the A over P to, I'm looking at when is F A to the P over E in the ideal generated by 1 over P to the E. Oh, sorry, no. I don't want in the ideal M, or the expansion of that ideal M, here we go. This ideal in S raised to the 1 over P to the A. That's S. So we're looking at sort of what power, it's kind of like a multiplicity in that sense. So what power is going to get in there? Okay, so that's the definition. Let me now say one more property, another property. We have sort of obvious upper and lower bounds on the F pure threshold. So now let me take an F in this polynomial again, polynomial ring again. And actually, to move things along and go a little quicker, maybe what I'll assume here is that F is homogeneous, because that's the case I'm ultimately going to focus on. So now I'm really going to look at the polynomial case. And then there's another obvious, or not quite obvious, but not so hard to prove property, which is that 1 over the degree of f is a lower bound for the f pure threshold of f. Again, at the unique homogeneous maximal ideal, and also the log canonical threshold if I were over C. And it's also got an upper bound of the number of variables over D. But of course, it also has an upper bound of 1, remember. So, or I could also write this as, let me make myself a little more room. Min 1 and n over D. D is the degree of my polynomial. So this on the, and by the way, if I were not in a graded situation, just in a local situation, I could get the same result here with working with the order of vanishing, the highest power, the lowest degree term of F instead of D. We'll still get that same statement. But let's just focus on this case. Now this equality here holds, maybe I'll put here, or LCTF. This equality, we know exactly when it holds. This holds if and only if. Oh, I might 2L, sorry. If is a power of a linear form. And we actually know some more things about lower bounds that I'm not going to get into, but that's one thing I just wanted to point out when we have this up here. And then another property we know on this side is that this holds. So what I meant by holds is equality holds. Sorry. And that's true for log canonical threshold and F pure threshold. Here we know that equalities sometimes holds. For the log canonical threshold when K is C. So in that world where we're dealing with the complex setting, we have equality here when, for example, sorry, let me write when nicer. One case where we know this holds is when the vanishing set of F, right, this lives inside of Cn now, has an isolated singularity. So this is sharp. The upper bound is sharp for in characteristic 0. And in fact, that's kind of it's achieved by kind of a generic F, right? If I take a totally random polynomial of degree D and n variables, it's going to cut out a smooth variety. And that for that, we know exactly what the F pure threshold is. It'll equal this theoretical largest possible thing. And so some natural questions arise. Is anything like this true in characteristic P? Do we have sharpness? Do we have any sharp upper bound, or, you know, is this a sharp upper bound in characteristic P? And you could ask other questions such as, is it also achieved by kind of a general, you know, a generic element of characteristic P? So let me go to the next slide and give you an example. So here's an example. So let's say that P is going to be arbitrary, but positive. And let's take D and N to be 3. So I'm talking about cubics in 3 variables that are homogeneous. So these are, maybe I write that, homogeneous cubics in 3 variables. Okay, so these are cutting out cubic curves in P2, right? And when they are cutting out a smooth curve, that's an elliptic curve. And so we can think of like the parameter space of all cubics of all such cubics. I mean, that's just a set. And it is equal to, or it's like, you know, we can think of it as, I'm going to think of it as the symmetric third symmetric power of the space of linear forms in 3 variables, right? Which is a vector space of dimension 10. So if I wanted, you know, when I compute the F pure threshold, you can see from the definition that scalar multiplying it by some non-zero value in K isn't going to change the F pure threshold. So it's natural to also do this up to scalar multiple. In which case we would be talking about the projective space of this thing, right? In other words, P9. So there's a projective 9-dimensional space of cubics of degree 3 and 3 variables. And what I'm asking here is basically, can we describe like a filtration or a stratification of P9 by the F pure threshold in such a way that we understand sort of exactly what's going on? So let's think about it in this example. A cubic will be something of the form, you know, ax cubed plus bx squared y. I'm not going to write all this out, but you guys know we have different variables. I think J is the 10th letter of the alphabet. So I have my cubic, or, you know, up to scalar multiple cubic corresponding to the point in here. A, B, dot, 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 up to J in P9. Sorry if this is messy. And here's a theorem, or here's a calculation due to Bargoff. It appears in a paper of Anurag Singh and Bargoff Bhatt, which is that if F defines, so let's call this F for a moment. So if the elliptic curve defined by F, V of F in P2 is smooth, so if the cubic cuts out an actual elliptic curve, a smooth guy, then we know what the F pure threshold is. The F pure threshold of F is either 1 or 1 minus P. This happens when this curve, let me call it E, the elliptic curve, capital E. When E is ordinary, or 1 minus 1 over P when E is not ordinary. Otherwise, so when E is what's called supersingular. Actually, I can remind you what supersingular means. What that means is if I compute the first check cohomology of the structure sheaf of the elliptic curve, that's a 1-dimensional space over K. And then I look at the action on that induced by Frobenius. That's just a map from a 1-dimensional K vector space to another one, and it's an abelian group map. And this is supersingular means that this is the 0 map. or is not injective. Maybe I'll say it that way. Same thing because it's a one-dimensional target source. All right. That's just what super singular means. This is well known to number theorists. But what this shows us is our bound. So let's remember what that bound was. We knew that the F pure threshold in general is always less than or equal to the minimum of 1. And in this case, D over N is 3/3. So this is F pure threshold of all of these cubics is less than or equal to 1. And so what we're seeing is this ordinary case, this is kind of the generic case. So this happens, this is a generic situation. And so for most of the elliptic curves, a randomly chosen cubic will define a smooth curve in P2, and it as an elliptic curve that will be an ordinary curve, and our F pure threshold will be 1. So we're getting that same sharp upper bound that we get for the log canonical threshold over the complex numbers. But we see now that some interesting things can happen even when we're smooth. In the smooth case over C, the elliptic curve, this is always 1. The F pure threshold, sorry, the log canonical threshold is always 1. Here we're getting something more interesting happening depending on the characteristic. But even in a fixed characteristic P, most of the curves have the generic value of 1 for the F pure threshold. And so it looks like maybe that upper bound is achieved in general. So let me write that here. In this case, so maybe I'll write when. So for D equals N equals 3 and arbitrary P, the upper bound FPT less than or equal to the min of 1 and D over N is sharp in every characteristic and achieved on a dense set. In fact, it's a dense open set, but I haven't justified that openness yet. But okay, so it looks like maybe it's true in general that we always get the same thing, and we do get a lot of the same facts for log canonical threshold and F pure threshold. Actually, maybe there was one thing I wanted to say about the equivalence or the analog feature of that, which maybe I'll say now. Recall that, what does it mean that it's an analog? I mean, it means it has a lot of the same properties, but it's even better than that. If I take a polynomial with integer coefficients, and it doesn't need to be integer coefficients, but just to keep things simple, I can look at F mod P, right? Reduce all the coefficients, mod P, and that is a polynomial in the polynomial ring over FP. And, you know, maybe look at it over the algebraic closure of that if you want, but it doesn't matter. And then we can compute the F pure threshold of that. There'll be a different value of that for every value of P at the so M here is not a maximal ideal anymore, but it's like relatively maximal. It's ideal generated by the X's. It'll be maximal once I go mod P. That's a whole big collection of values, one for each P, and all of them are less than the log canonical threshold of the same F, thinking of it over C. So I can view a polynomial with integer coefficients as a polynomial with complex coefficients, and as such, I can compute its log canonical threshold at that same point, that same maximal ideal. And all of those F pure thresholds will be less than or equal to this. And in fact, this, if I take the supremum of these, I will have an equality. So this is what one of the things I meant on the previous slide when I said that we have an analog, and this is a very good approximation. So it's not unreasonable to expect that if we know this guy is bounded always and sharp for some values of D and N, that maybe the same thing is true for these F pure thresholds in some P's. But it turns out that is not true. So it turns out, and that's one of the things I'll explain. The F pure threshold of F less than or equal to this bound, this upper bound, is not sharp. In each fixed P. It's sharp in some P, but if I fix a P, it might not be sharp. Maybe I should say in some P's. By the way, it's a conjecture whether we have an equality of the F pure threshold mod P with the log canonical threshold for infinitely many P. But I will explain this. What Adela and I do one of the things we do is we compute the we give a formula for the maximum value of the F pure thresholds over all F where F is a polynomial in a polynomial ring of characteristic P. The K doesn't matter, but we have degree D, n variables, and fixed characteristic P. So it's a number that depends on all D, N, and P. And we know exactly when it's equal to this min. And when it isn't, we know exactly what it is. It's a truncation of the base P expansion of D over N. And I'll explain it in a few minutes. But I just wanted to get to the point of what this is one of our main results, is an explicit formula for this.
Karen, shouldn't it be N over D instead of
Absolutely.
Okay, I was just making sure.
When did I do yeah, absolutely. Did I have that wrong on all the slides?
I think it was only once before.
Thank you to whoever pointed that out. I should maybe fix it since this is for posterity, right? My apologies. I am a little bit frazzled. Oh, it's everywhere. No, this one's right. Okay, the first time I said it right, but then I went off the rails. Okay. Oh, here's I'm wrong here too. All right. I mean, one way to think about it is if you fix n, so you're looking at polynomials, or you can think of it as hypersurfaces in a projective space, a fixed projective space, and you let D get larger and larger and larger, those hypersurfaces are getting higher and higher multiplicities. They're getting more and more singular. So the F pure thresholds are getting smaller and smaller. The smaller the F pure threshold is, the more singular your hypersurface is supposed to be. It's one, the largest it can be, if and only if you're Frobenius split, and otherwise it's kind of a measurement of how far it is from being Frobenius split. All right, so let me now slightly change the topic temporarily. We will come back to stating that theorem carefully in a moment, but I want to talk about stratifying this projective space of polynomials, or you can think of it as degree D forms in n variables. Sorry about the pedantry, but I like to think of that as dual space because it's forms. Stratifying this projective space of degree D forms in n variables. Up to scalar multiple, which I wrote right, that's what the P means, right? By F pure threshold. So K is a fixed field of some fixed characteristic P, and to avoid special extra hypotheses that don't matter very much, assume that K is algebraically closed. This is a projective space. And let's first make the following observation. I'll call it a proposition. If I fix a lambda in R, some positive number, then the set X less than or equal to lambda, by which I mean I'm going to take the set of all polynomials in the projective space. How about I just call this thing capital P? Since I'm trying to write with my mouse. This big projective space of all degree D forms in n variables, I look at the ones whose F pure threshold is at the maximal ideal, of course, unique homogeneous maximal ideal is less than or equal to lambda. Let's look at this set. This set is closed. So I want to justify that. So case one, let's assume that we are dealing with a lambda of the form some A over a power of P. This special kind of lambda. Let's look at those. So for a lambda of this type, remembering our definition, the F pure threshold of F is going to be less than or equal to A over P, A over P to the E, if and only if F to the A is in the P to the E Frobenius power of the maximal ideal. That's because the F pure threshold, remember what it was, it is the infimum of all the A over APs with this property, right? Maybe I'll just write it out. I'm just reminding you the definition. So just by definition of infimum. That's what the F pure threshold being less than that number means. And now this is a closed condition. If I think about it, if I write F as some sum over all indices, multi-indices, for of not less than or equal to, these are equal to D. So I have, monomials of degree I, homogeneous of degree I, but there's lots of them. And they have some coefficients here. These AIs are the homogeneous coordinates of that big projective space. That capital P up here. Before I wrote them out, they were like A through J when we were dealing with cubics. And when we write A that way, All we need to do is then think about when I raise f to the capital eighth power here, this is going to be some other big sum, right? It'll be of degree a times d, right? And there'll be some coefficients here, c, that are polynomials in the a's. So I'm going to write c capital N just to remind me of how many variables I'm in, and j to index which monomial I'm talking about. So these c's are homogeneous polynomials. In the a's. So in order for f to the a to be in that p to the e Frobenius power, what we want is that certain ones of those c's are vanishing, right? This is going to hold if and only if cj, when I plug in a specific, values of my ai's, the coefficients of my f, these should be 0 for the j's. This j is a multi-index. We have the n variables, and it should be vanishing when all the ji's are less than or equal to p to the e minus 1. So jk for all k in the set 1 to n. Does that make sense? Hopefully you can read that. Was it capital E? All I'm saying is this is a closed condition. I'm describing what the polynomials are. Maybe it's not really worth it at the moment to see that this is a closed set. But then what we see is that this x lambda is just defined by these c's. AD and the individual j's are less than or equal to p to the e minus 1. And that's a closed subset of our big projective space. This is the projective space of all polynomials homogeneous of degree d in n variables. All right, so it could be empty. And sorry, that should be a less than or equal to lambda, not equal lambda, less than or equal to. So that's if we have this first case where lambda is a rational number with p to the e in the denominator. If it's not, if lambda is not of that form, what we're going to do is we're going to approximate it by elements of that form. So what we're going to do is we're going to think of lambda is the limit of a decreasing sequence, or I guess I should say non-increasing sequence so I've got lambda multiplied by p, rounded up, divided by p, and then I've got do it with p squared. And then do that forever. Lambda is obviously smaller than all of these, and they're obviously converging to lambda as e goes to infinity, as we take more and more powers. And so what's happening is, if I think about these closed sets now, now these guys are all rational numbers with p to the e in the denominator, right? So we just proved that these are closed sets. And these are getting smaller. Well, they might be stabilizing. Of course, they will stabilize at some point because I'm in a variety. I mean, the Noetherian property will eventually make these stabilize. And when they stabilize, they're all going to contain the guy that we're interested in. and it will equal one of them. Does that make sense? So in other words, I can think of my x less than or equal to lambda as the intersection of all of these. And an intersection of closed sets is closed. All right. So this is a closed set. And similarly, so a corollary, which maybe I won't prove explicitly right now because I'm running out of time for these kind of details, but I'll point out that x lambda, which is the set where we're equal. This is a set of all polynomials of whatever degree, let's say degree D, in however many variables, whose F pure threshold is equal to lambda. This is a locally closed set. Which isn't too hard to see from where we're at, and I will skip that. Of course, it's probably empty most of the time. It could be empty because not every number can be the F pure threshold of something. In fact, there's only finitely many numbers that can be the F pure threshold for a fixed D and N and P. Yeah, actually, there was one interesting point in the proof of this. Maybe I'll skip it anyway, and I'll review the point that was going to come up, because it will help me state our theorem. Let's say the following. Let's fix any lambda now that could be an F pure threshold. So it's got to be something in between 0 and 1. It might equal 1. It's a real number between 0 and 1. And we can write it in base P. I can do this, of course, for any real number, but I want to just keep the notation simple. P being the characteristic of our ground field. So when I do that, I'm going to have lambda equals some digit over P plus some digit over P squared, and so forth, right? Where these guys are going to be always numbers between 0, 1, and P minus 1. So for lambdas of the form that we were just thinking about, for lambdas of this special form, there are two such ways to write this. Two such base P expansions. Right, just like we can write 1 as 0.9999 forever. The same thing's true here. So for example, 1 over P is 1 over P, which is 0 over P plus you see what I mean? Because this part of it is sorry, eraser. Because this is the same as 1 over P times P minus 1 times 1 over P plus 1 over P squared. Did I mess that up? Whatever. I'm going to let you guys do that simple math. These two expansions are the same, right? There's two different ways to do that. However, one of these you see is terminating. This is a terminating. Base P expansion. And the other one is a non-terminating. Actually, the importance of this idea I learned when Daniel Hernandez taught me when he was writing his PhD thesis, non-terminating base P expansion. Every real number has a unique non-terminating base P expansion. And that is super important in understanding the question I'm describing. Yeah, so that actually gets used in proving that the set of hypersurfaces of degree D in n variables whose F pure threshold is exactly lambda is a locally closed set. Okay, so let me now go to the next slide and describe another corollary of what we were talking about, which is that this projective space of degree D guys, homogeneous forms in n variables has a finite stratification by F pure threshold. So in other words, I'm going to write it this way. Again, I'm going to call this thing P. P is equal to, first of all, the set of all, I mean, there's some maximal. So, well, let me just write this thing first. There exists a set lambda 1 through lambda t of rational numbers such that each of these guys is properly contained in the predecessor. Here is the minimal ones, which is actually equal to, because nothing can be smaller, that last one. And each one of these lambda i's minus lambda, the next one on the list is non-empty. So, I mean, I've just like basically said, these are the exact values of there's a finite list of rational numbers that can be the F pure threshold of a polynomial in D variables, sorry, in N variables of degree D, homogeneous polynomial. And this first one, we have a formula for. By the way, maybe I should say here that, yeah.
Yeah. So this is for a fixed degree D, this like this chain, right?
Yes.
Yeah. So that in particular, aren't you kind of claiming that for a fixed D, the supremum is actually a maximum for a pure threshold?
I'm not sure
Because-
exactly what you mean. There is a number here that's achieved, which is the maximum possible F pure threshold, the generic F pure threshold. Or the F pure threshold is I'm not sure what you mean exactly.
Okay, for a fixed D. I see. Okay, no problem.
These lambdas are not of the form A over P to the E. Is that what you're thinking?
Yeah.
These are not. These lambdas are not of the form. I mean, actually, most of them are, but one of them is not. Let me keep going. Let me explain what I mean. So yeah, I think you're thinking about the definition, and I'm not referring to any particular A over P to the E's in these definitions here. I mean, in this chain here.
Yeah. Okay.
Okay, so So I wanted to mention, though, a really nice result of Sato that makes part of this clear for other reasons, which is this ACC for F pure thresholds theorem. If I fix if I fix any regular ring of dimension n and ask about what are the possible F pure thresholds, that set of possible F pure thresholds has the ascending chain condition. So when I further restrict myself to homogeneous polynomials of degree D, which has the descending chain condition, we see that there's going to be only finitely many possible values of the F pure threshold. So let me write this was DCC for degree D homogeneous. Then we get that there's finitely many. So what we do is give you a formula, or one of the things we do is an exact formula for this top value. So this top value here, let's call, so these are the exact values, these lambda are the exact values of F pure thresholds. The possible values of F pure thresholds here. And so so maybe I should go to the next page and state the theorem, since I'm basically out of time. So I want to fix P, the characteristic of the ground field, and fix D, the number of variables, and fix N. Sorry, D is the degree, N is the number of variables. And so the maximum value of the F pure threshold of a degree D form homogeneous polynomial in n variables, that's not a W, that's an N, over a field K of characteristic P. And I think I better assume it's algebraically closed for this. Let me try to state what it is clearly. Well, there's sort of two cases. So first of all, if n is bigger than or equal to D, then it's, oh, and by the way, this maximum value is also the generic value. A generic polynomial will have this maximum value by the previous slide, right? So I also think of it as kind of the generic F pure threshold for polynomial of this degree and number of variables. So if n is greater than D, this max FPT is 1. Always. So we saw that in the case of the elliptic curve. Remember when we had D and N were both 3, we saw that we always could find the generic curve or the generic form of degree 3 had an F pure threshold of 1. And for n less than D, or actually the formula also works when n equals D, so maybe I'll write it both ways. What we want to do is we want to consider this number n over D, and which is a rational number, And we want to ask if there exists an L, which is going to be a natural number, such that two things hold. This is not an integer. So in other words, n over d does not have denominator power of p. And this is the non-trivial part of it, the remainder, it looks a little funny, but I want to state it. The remainder, when we look at this fraction, so we have p times L times n, that integer is divided by d. Now, the remainder is always a number between 0, including possibly 0, and strictly less than d. But if it's less than n, strictly less than n, if there exists such an L, then the maximum F pure threshold, which you again can think of the F pure threshold of a generic polynomial in this number of variables, is equal to the truncation of the non-terminating, remember there's a unique non-terminating expansion. Or maybe I didn't even need to say that because I'm assuming I'm not have a denominator where I might have a terminating one. But anyway, the F pure threshold, the maximum F pure threshold is the truncation of the non-terminating expansion, base P expansion of n over d for the smallest possible, for smallest such L. Sorry, I should have said that for the smallest L. Right, so if there is an L, take the smallest one with these properties and then truncate the bound you get for the log canonical threshold at that spot. The Lth truncation. And that is your maximum F pure threshold. If no such L exists, then the maximum F pure threshold is equal to the one we expect in characteristic 0, the one we get from the log canonical threshold, which is n over d. Does that make sense? It's kind of a mouthful, but it's actually pretty concrete. I give you one example. Suppose that P is congruent to 1 mod D. And D is less than or equal to the number of variables. So relatively low degree form. No, that's backwards. So in this case, the F pure threshold of the maximum possible. Maybe I'll write it this way. This is always less than or equal to n over d, as we know from before, with equality. That's just the same bound we had before, but we have equality.
I think we just lost. Karen, are you still there? All right, I'm gonna pause the recording for just a second.
I'm very sorry. Oh, I think I shared it wrong, but that's okay. I was saying that if we happen to be in a situation where the characteristic is congruent to 1 mod the degree, then we can say that we have the generic F-pure threshold, the maximum possible F-pure threshold is exactly equal to the expected one for the log canonical threshold in characteristic 0. We get that equality in a dense open set of the parameter space of all degree D guys. And the proof is real simple, because if P is congruent to 1 mod D, then if I multiply by the, so that means that P to the L is also congruent to 1 mod D, raising everything to the Lth power in Z mod D. And then when I multiply by N, I have N P to the L is congruent to N mod D. And in other words, this is our remainder, right? This is the remainder when N P to the L is divided by D, and N is less than D. The remainder is, oh wait, sorry, I've got this backwards here. I'm sorry, I got confused by dropping out. This is actually 1 in our case, right? The remainder is always N. The remainder is always N, which is not less than N, not less than N. So according to our theorem, that when we're less than N is exactly when we would have a truncation. So here we don't have a truncation. This is irrelevant. In fact, sorry, I'm messing up, guys. Sorry, I was panicking because of the time and stuff. So this is why we're getting that, because there is no value of L that has that property we want. There's no L that it works for. We have to go with no truncation at all. In other words, this guy is our maximum possible F-pure threshold. So by the theorem that Adela and I proved, and it's pretty technical, I'm not going to obviously say anything about the proof at this point. We know that the F-pure threshold, the max F-pure threshold, which is the value of the generic polynomials F-pure threshold, is equal to the N over D. All right, so and you can, there's many other like special cases you can get, and we know we worked them all out up to degree 8 or 9, exactly what the F-pure thresholds can be in every characteristic. Daniel Hernandez, Emily Witt, Luis Nunez, and Wenliang Zhang have a paper where they study F-pure thresholds for polynomials in 2 variables. And they ask some questions there that we give negative answers to using this theorem But we also, they also had very good insight into what they could be. They just didn't quite get it right. We kind of tweak what they do and get kind of a list of what they can be. But there's still lots of open questions even there about whether possible F-pure thresholds can be. So they're always either this number, N over D, or a truncation. And the question is, what truncations can they be?
Okay.
So I'm gonna quit. Sorry, I went over, guys.
No, I think that's totally okay. All right, let's all thank Karen.
Am I getting those little emojis or something?
Yeah, I see some of them up here. Are
I'm
there
so
any
done with the pandemic, guys. Thank you for thank you.
are there any questions? So, I mean, have you thought about what happens when you're not quite in a polynomial ring in some sense for any of this stuff?
A little bit. It's a lot harder. You mean like in a regular, just like a regular local ring and seeing if you can get bounds and stuff?
Yeah, or even not. I mean, yeah, sure, or even not
So,
regular or something.
Okay, you probably can't see my screen. Let me share it again.
We can see a Jamboard still.
Oh, you can still see it? Okay, I can't tell that I'm sharing. Okay, so for example, if you just look at like non-homogeneous polynomials, like
Oh,
something
sure.
like this,
Yeah,
like the F-pure thresholds cluster,
yeah, they're most, yeah. Mhm.
so I mean, this does not have DCC.
Mhm.
This set of F-pure thresholds in a polynomial, even if I take just a polynomial ring but don't require homogeneity, you don't have DCC. Like, these are a subset of, these are the F-pure thresholds, and we
Yep.
see that
Yep,
we
yep.
have an infinite chain. So that means like a lot of what we're
See.
thinking about like just isn't gonna work nicely. There's no lower bound. Like, I
Yeah.
mean, these
Yeah,
are approaching, I guess,
half.
1/2.
Yeah,
But yeah, anyway,
okay.
so we've thought a little bit about it and gotten discouraged. We haven't thought deeply about it, and we were planning to come back to it eventually, but yeah, we got discouraged by things, but like phenomena like this.
I see, okay.
Like, so for example, for homogeneous guys, that there's a lower bound. If F is homogeneous of degree D,
Mhm.
and reduced, so no repeated factors, because that definitely complicates things when you have repeated factors, then the F-pure threshold is always bounded below by 1 over D minus 1. So this is a paper with a whole bunch of people. I'm gonna fail on spelling catastrophe. I'm not gonna try. Zhibek. A whole bunch of people are in here. Janet Page, Emily Witt, Adela Me, Jyoti Singh, Zhibek, Jenny Kenkel. I think I said all the names. So we proved this lower bound, but see, this, and we know exactly when it's with equality. So this is a sharp bound, and you have equality exactly when F can be written as well, F is in a Frobenius power, and it has degree equal to 1 more than the Frobenius power. It's a Frobenius form. But nothing like this is working in here, like for these kind of situations, these kind of examples. So yeah, I haven't thought about it deeply, but one could certainly ask these questions.
Are there any other questions?
Wait, so in the two variable case, you are saying the other values, other possible values of the pure threshold, that those will be truncation of this maximum value. And so how do the truncations look like? Are those still combinatorial in nature, depending on this P D and N. Sorry, N is 2, so P and D.
Uh-oh, wait. How do I, so I want to go back to the slide you're referring to. You're asking me which truncations happen?
Yeah.
So can you guys see my Jamboard? Do you see my Jamboard?
Yes, yes.
Okay, sorry, I think I have a bad connection or something. So this maximum one here, I'll put it in red, that's given by our formula. And then these other ones are all truncations. These are all this one might also be a truncation, but it might not. So this one is either N over D or a truncation given by our formula. And we tell you exactly what truncation. And then all the further ones are further truncations. And we don't really know what truncations there are. We know some truncations that always happen. But I don't think I have time to like write it down. It's a little bit technical. But in general, and we know actually another interesting thing that we know, if D is greater than 4 and P doesn't divide the degree D, then there's definitely always some further truncation. There's always some, like this is like a non-trivial filtration. So we know things like that, but we don't know a complete list of the truncations that can happen. In
Okay.
2 variables, Daniel and his collaborators had conjectured a complete list, and it is not that we know that. Anyway, yeah, it's still we don't know a full description of what all those truncations can be.
Right, but is the description of the truncation still combinatorial in nature, or is it? Do you have an example where it's not?
Combinatorial, yes, it is based on residue classes, mod P, and stuff like that. If that's what you mean by combinatorial.
Exactly. So, do you have any example where it's not of that form, but it's actually depends on what do I want to say?
No.
Okay. Okay. See, thank you.
Mhm.
Any final questions? Oh, Swaraj?
Yeah, so in the can you hear me?
I can hear you.
Okay, yeah, in the D less than or equal to N case, we know that the generic, so there is a dense set of hypersurfaces for which achieves the generic N over D FPR or FPR threshold, right? Not N over D, but maybe 1.
Sorry, you broke up, Suraj, but we know that there's it's an open this set of where you have the maximum F pure threshold,
Right.
minus the next possible F pure threshold. This is a closed set. Then sorry, let me fix this. This is always open. Is that what you were asking?
Right. So my question was in the.
So this is, in other words, X max. Sorry, I didn't hear you. I think you broke up. Did you say
Yeah.
something?
Yeah, my question was, do we know in the N when the FPR threshold, the maximum FPR threshold is 1? Do we know when this X max contains all these smooth hypersurfaces? Or the
It usually doesn't. It usually doesn't.
Okay,
Yeah, almost never, I would say.
I see.
Yeah, almost never.
Okay, thank you.
Yeah, I mean, like for the elliptic curve case, they're all, in every characteristic, there's always some non-super singular ones. Sorry, there's always some super singular ones. And so those are all smooth, but they don't have the max. The max is 1 there. Their F pure threshold is 1 minus 1 over P.
Okay, thank you.
Yeah, it almost never. Another example, in two variables, smooth is the same as reduced. And if D is greater than 4 and not divisible by P, the characteristic, then we know that there are always reduced ones that have some truncation there that are definitely not N over D. Oh, but you were just asking when D equals N. Is that what you were asking? Just when D equals N? Even in
Yeah.
that case, it's not true in general. I mean, the elliptic curve case is a counterexample of that.
Okay, yeah, thank you.
Yeah.
Trevor, you have a question?
Yes. So first thing is just like to ask-
Trevor, is there any way you can move your microphone a little closer? Because I'm having a hard time hearing you.
yeah, can you hear me now?
I can hear
Sort
you.
of. Okay.
Okay. So just to more clarify the question that Swaraj had, wouldn't it be true that like there's no that the maximal value happens all the time if those coefficients were like constant values, and so there was like when you were saying that the x lambdas are closed and you were looking at these equations of these vanishings of these coefficients as polynomials in the coefficients, wouldn't it be that like if those were never zero, if those were like constants, then you would always
Well,
have-
they're not usually going to be constants.
yeah,
They have some specific degree.
yeah.
Those
so it's like-
polynomials are homogeneous polynomials in the.
yeah, exactly. And so it's like never gonna happen. Almost like it's almost never gonna happen that these are always.
I'm not exactly sure what your question is, but it's a very non-trivial thing to figure out when the set that they define is empty or not empty.
Okay.
And maybe that's related to what you're asking.
Okay. Yeah. My second question is about whether you think your methods here would generalize to homogeneous with respect to a non-standard grading.
Do you mean where the degrees of the variables do not have, or not all degree 1?
Precisely.
Is that what you mean? You're still graded by the integers, but
Yes.
is that what you're saying?
Yes.
Yes, you can probably do something. Actually, Daniel Hernandez and his collaborators have various papers looking at these things, and they also consider non-standard gradings. Yes. So I don't know if we haven't tried to work out a formula in that case for ours. But the methods are probably adaptable. But if
Okay.
you had grading by some other group, like that would be a lot harder. You know, not an N grading, but some other grading. I'm not so sure what to do.
Okay. Thank you.
I guess I was approaching it from the point of view of thinking about hypersurfaces and projective space. Pretty concrete. And yeah, but you could of course do hypersurfaces in weighted projective space.
Okay. Thank you.
Mm-hmm. Yeah, somebody should go and adapt it. I bet you can do that.
Okay, any other questions? Yeah. All right, well, if not, let's thank Karen again. And
Thanks for the little clappy hands.